Now we present an important thermodynamic process called Carnot Cycle, which is a theoretical model describing the thermodynamic cycle converting heat to work in steam engines. When we introduced the concept of thermodynamic cycle, we defined it as a connected sequence of thermodynamic processes, where the initial state of the first process in the sequence is the same as the final state of the last process in the sequence. As an illustration, we also showed the state space of the system where the thermodynamic cycle takes place. In the state space spanned by the axes of the state variables x1, x2, ellipsis, xn, the intermediate states of the thermodynamic cycle are represented by the points p1, p2 and p3. These states are connected with the path calligraphic p in the state space, which represents the cycle. We started the historical remarks on the concept of thermodynamic system with Nicolas Leonard Sadi Carnot, who studied steam engines to improve their performance in the conversion of a given amount of heat to mechanical work. In his book published in 1824, Carnot defined a theoretical heat engine shown in the cross-sectional diagram, where he considered the body of the water vapor or the working substance as an ideal gas in the cylindrical vessel of the steam engine with a frictionless piston, and the bodies A and B of constant temperature, which are the thermal reservoirs or baths brought into contact with the cylinder. He examined the thermodynamic cycle taking place in such a system, which is called Carnot cycle. Carnot cycle consists of four thermodynamic processes: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. We label the processes with the numbers from 1 to 4, starting with the isothermal expansion of the working substance. Since Carnot cycle is a sequence of idealized thermodynamic processes, all of them are supposed to be quasi-static. This means the following. The ideal gas law holds throughout the cycle, and the difference delta P between the internal pressure in the cylinder and the external pressure in the surroundings is small. In other words, the ratio of the magnitude of delta P to the external pressure is much smaller than 1. Similarly, the difference delta T between the temperature of the gas and the temperatures of the heat baths is also small, that is, the ratio of the magnitude of delta T to the temperatures of the heat baths is much smaller than 1. Now we examine all the four processes in Carnot cycle. The first process in the cycle is an isothermal expansion of a given amount of ideal gas in the cylinder, which is brought into contact with a heat reservoir of the absolute temperature T1. After the gas reaches thermal equilibrium with the reservoir, its absolute temperature becomes T1. The pressure PA and the volume VA of the gas at the absolute temperature T1 are the initial state variables of the gas in its initial state denoted by the letter A. If the external pressure is somewhat smaller than the pressure of the gas in the cylinder, the gas will undergo a quasi-static isothermal expansion. Then the initial volume VA of the expanding gas increases to the volume VB when it reaches its final state of the isothermal expansion denoted by the letter B. At the same time, its initial pressure PA drops to the pressure PB, while its absolute temperature T1 remains the same. During its isothermal expansion, the gas absorbs the heat Q1, and does the pressure volume work W'1 on the surroundings. We can illustrate the quasi-static isothermal expansion of the gas in the pressure volume diagram, where the family of the rectangular hyperbolas represent the isotherms of the given amount of ideal gas in the cylinder. Let us suppose that one of the isotherm represents the isothermal process of the gas at the absolute temperature T1. Then the initial state A and the final state B of the gas undergone the isothermal expansion lie on this isotherm, and the process is represented by the green curve on the hyperbola between the points A and B. The arrow indicates the direction of the process pointing from its initial state A to its final state B. We can calculate the heat Q1 absorbed by the gas during its isothermal expansion. Since the temperature of the gas is constant, its internal energy does not change in the process. Then the first law of thermodynamics states that the heat Q1 is equal to the work W'1 done by the gas, which can be written as the mass m of the gas, times its specific gas constant Rs, times its absolute temperature T1, times the natural logarithm of the ratio of its final volume VB to its initial volume VA. Since the final volume of the expanding gas is greater than its initial volume, the heat Q1 and the volume W'1 are positive. The second process in Carnot cycle is an adiabatic expansion of the gas in the cylinder. Here the gas in the cylinder is thermally insulated, preventing the exchange of heat between the gas and the surroundings. If the external pressure is still somewhat smaller than the pressure PB of the gas, then the gas will undergo an quasi-static adiabatic expansion. Since the expanding gas cannot absorb heat, it will cool down and its absolute temperature T1 drops to the absolute temperature T2 in the final state of the adiabatic expansion denoted by the letter C. The initial volume Vb of the expanding gas increases to the final volume Vc, whereas its initial pressure Pb reduces to the final pressure Pc. The expanding gas does the pressure volume work W'2 on the surroundings. In the pressure volume diagram, the adiabatic expansion of the gas is represented by a path along an adiabat passing through the point B. The adiabat depicted with the yellow curve is steeper than the isotherm of the absolute temperature T1, intersecting the adiabat in the point B. The path of the adiabatic expansion is represented by the orange color curve running between the initial state B and the final state C of the process. The arrow indicating the direction of the process points from the point B to the point C. The final state C of the gas lies on another isotherm of the absolute temperature T2, which is smaller than the initial temperature T1 of the gas. Since there is no heat exchange between the gas and the surroundings during the adiabatic expansion of the gas, the first law states that the pressure volume work W'2 done by the gas is equal to the change in its internal energy, which can be written as the mass m of the gas, times its specific heat capacity Cv for a constant volume, times the difference between its initial temperature T1 and its final temperature T2. The work W'2 is also positive, due to the fact that the initial temperature of the cooling gas is greater than its final temperature. After the isothermal and the adiabatic expansion of the gas, the next two processes in Carnot cycle apply compression so that the gas could be brought into its initial state. The third process in the cycle is an isothermal compression of the gas, where the gas is brought into contact with the heat reservoir of the absolute temperature T2. Since the temperature T1 is greater than the temperature T2, the heat bath used in the first process, that is in the isothermal expansion of the gas, is also called hot reservoir, whereas the heat bath used in this process is called cold reservoir. If the gas remains in thermal equilibrium with the cold reservoir, then its temperature is constant during the process, that is, the absolute temperature of the gas is equal to T2. Now the state C is the initial state of the gas in the compression, and its pressure Pc and volume Vc at the absolute temperature T2 are the initial state variables of the gas. We can compress the gas in a quasi-static process by moving the piston slowly enough. Then the initial volume Vc of the gas is reduced to the volume Vd when it reaches its final state denoted by the letter D. At the same time, its initial pressure Pc increases to the pressure Pd, while its absolute temperature T2 remains the same. Here we suppose that the final state D of the gas is such a state, which allows the gas to return to the state A in an adiabatic compression. During its isothermal compression, the gas releases the heat minus Q'2 to the cold reservoir, where Q'2 is positive. The minus sign indicates that the heat flows out from the gas, extracting energy from the system. The moving piston does some work on the gas, that is, the pressure volume work W'3 done by the gas on the surroundings is negative. In the pressure volume diagram, the initial state C and the final state D of the gas undergone the isothermal compression lie on the isotherm of the absolute temperature T2, and the process is represented by the purple curve on the hyperbola between the points C and D. The arrow on the curve points from the state C to the state D, which is the opposite direction of the isothermal expansion between the states A and B. We can calculate the heat Q'2 released by the gas during its isothermal compression. From the first law of thermodynamics we obtain that minus the heat Q'2 is equal to the work W'3 done by the gas, because the internal energy of the gas remains constant. The work can be written as the mass m of the gas, times its specific gas constant Rs, times its absolute temperature T2, times the natural logarithm of the ratio of its final volume Vd to its initial volume Vc. Since the initial volume of the compressed gas is greater than its final volume, minus the heat Q2 and the work W'3 are negative. The last process in Carnot cycle is an adiabatic compression of the gas. Here the gas in the cylinder is thermally insulated as in the case of its adiabatic expansion, and there is no exchange of heat between the gas and the surroundings. If we compress the gas by moving the piston slowly enough, then the gas will undergo a quasi-static process. Since the gas cannot release heat during its compression, it will warm up, and its absolute temperature T2 increases to the absolute temperature T1 in the final state of the process, which is the initial state A of the cycle. During the compression, the initial volume Vd of the gas decreases to the volume Va, whereas its initial pressure Pd increases to the pressure Pa. At the same time, the pressure volume work W'4 is done by the gases minus the work done on the gas by the moving piston. As already mentioned, the choice of the state D of the gas is such that the adiabat passing through it also passes through the state A, which is depicted by the yellow curve connecting these states in the pressure volume diagram. Therefore, The adiabatic compression of the gas is represented by a blue color path along this adiabat between its initial state D and its final state A. The direction of the process is the opposite of the direction of the adiabatic expansion of the gas, as indicated by the arrow. There is no heat exchange between the gas and the surroundings during the adiabatic compression of the gas. As a result, the first law reduces to the equation stating that the pressure volume work W'4 done by the gas is equal to the change in its internal energy, which can be written as the mass m of the gas, times its specific heat capacity Cv for a constant volume, times the difference between its initial temperature T2 and its final temperature T1. This is equal to minus m times Cv times the difference between T1 and T2. The work W'4 is negative, since the final temperature T1 is greater than the initial temperature T2 for the warming gas. After determining the work done in each process, we can compute the net work done in Carnot cycle. The net work W' done by the gas is simply the sum of the work done in each process, that is the work W'1 and the work W'2 done by the system during the expansion of the gas, and the work W'3 and the work W'4 done by the system during the compression of the gas. The work done during all the four processes of the cycle will be shown in this table. In the first process, where the gas is brought from the state A to the state B at an isothermal expansion at the absolute temperature T1, the work W'1 is equal to the mass m of the gas, times its specific gas constant Rs, times its absolute temperature T1, times the natural logarithm of the ratio of its final volume Vb to its initial volume Va. This work done by the expanding gas is positive. In the second process, where the gas is brought from the state B to the state C in an adiabatic expansion, the work W'2 is given by the mass m of the gas, times its specific heat capacity Cv for a constant volume, times the difference between its initial absolute temperature T1 and its final absolute temperature T2. This work done by the expanding gas is positive. In the third process, where the gas is brought from the state C to the state D in an isothermal compression at the absolute temperature T2, the work W'3 is equal to the mass m of the gas, times its specific gas constant Rs, times its absolute temperature T2, times the natural logarithm of the ratio of its final volume Vd to its initial volume Vc. Since the gas undergoes a compression, the work W'3 done by the gas is negative. In the fourth process, where the gas is brought from the state D to the state A in an adiabatic compression, the work W'4 is given by minus the mass m of the gas, times its specific heat capacity Cv for a constant volume, times the difference between its final absolute temperature T1 and its initial absolute temperature T2. Since the gas undergoes a compression, the work W'4 done by the gas is negative. Here we can see that the work W'2 done in the adiabatic expansion is equal to minus the work W'4 done in the adiabatic compression. Therefore, they cancel each other out in the sum. As a result, the net work W' done by the system is equal to m times Rs times T1, times the natural logarithm of the ratio of Vb to Va, plus the m times Rs times T2, times the natural logarithm of the ratio of Vd to Vc. Since both terms in the sum are greater than 0, the net work W' is positive. Here we can use one of Poisson's equations derived for an adiabatic process in an ideal gas stating that the absolute temperature T of the gas, times its volume V raised to the adiabatic index gamma of the gas minus 1 is constant in the whole process. If we apply this equation for the adiabatic expansion of the ideal gas in Carnot cycle, then we can write that the initial absolute temperature T1 of the gas, times its initial volume Vb to gamma minus 1 is equal to its final absolute temperature T2, times its final volume Vc to gamma minus 1. Similarly, we can apply Poisson's equation for the adiabatic compression of the ideal gas in Carnot cycle. Then we state that the final absolute temperature T1 of the gas, times its final volume Va to gamma minus 1 is equal to its initial absolute temperature T2, times its initial volume Vd to gamma minus 1. If we express the ratio of the absolute temperature T1 to the absolute temperature T2 from these equations, we obtain the following equations. First, this ratio is equal to the ratio of Vc to Vb raised to gamma minus 1. Second, this ratio is also equal to the ratio of Vd to Va raised to gamma minus 1. As a result, the expressions in the right-hand side of these equations are equal, and we can write that the ratio of the volume Vc to the volume Vd is equal to the ratio of the volume Vd to the volume Va. Therefore, the ratio of the volume Va to the volume Vb is equal to the ratio of the volume Vd to the volume Vc. Now we can substitute this result into the net work W' done by the gas, which gives m times Rs times T1, times the natural logarithm of the ratio of Vb to Va, plus the m times Rs times T2, times the natural logarithm of the ratio of Va to Vb. Since the logarithm of a fraction is equal to minus the logarithm of the reciprocal of that fraction, we can write the right-hand side as m times Rs, times the difference between T1 and T2, times the natural logarithm of the ratio of Vb to Va. This expression is also equal to m times Rs, times the difference between T1 and T2, times the natural logarithm of the ratio of Vd to Vc, which shows that in order to determine the net work W' done in Carnot cycle, we can use the initial and the final volume of the gas either in the isothermal expansion or the isothermal compression of the cycle. We can also obtain the work done in the whole Carnot cycle by evaluating the pressure-volume integral from the area of its graph in the pressure-volume diagram. The pressure-volume work W' done by the gas in the whole cycle is given by the contour integral of the pressure P of the gas as a function of its volume V with respect to the volume V along the path of Carnot cycle. In the pressure-volume diagram, the path is represented by the closed curve connecting the points A, B, C and D. The contour integral along this path is equal to the area of the plane figure defined by this closed curve. It is easy to show that W' is given by this area, if we split the contour integral to the terms of each process in the cycle. In the first process represented by the curve connecting the points A and B in the pressure-volume diagram, the work W'1 done by the system is equal to the integral of the pressure P with respect to the volume V from the initial volume VA of the system to its final volume VB. This integral is equal to the green area of the plane figure under the curve connecting the points A and B. Similarly, in the second process represented by the curve connecting the points B and C, the work W'2 done by the system is equal to the integral of the pressure P with respect to the volume V from the initial volume VB of the system to its final volume VC. This integral is equal to the blue area of the plane figure under the curve connecting the points B and C. The total work done by the two processes is the sum of the work W'1 and the work W'2. Since the direction of the integration along these two curves indicated by the arrows is positive, the integrals, that is the areas under the curves, are also positive. As a result, the total work done in these processes is positive. Now we consider the second two processes in Carnot cycle. In the third process represented by the curve connecting the points C and D in the pressure-volume diagram, the work W'3 done by the system is equal to the integral of the pressure P with respect to the volume V from the initial volume VC of the system to its final volume VD. This integral is equal to the blue area of the plane figure under the curve connecting the points C and D. Similarly, in the fourth process represented by the curve connecting the points D and A, the work W'4 done by the system is equal to the integral of the pressure P with respect to the volume V from the initial volume VD of the system to its final volume VA. This integral is equal to the green area of the plane figure under the curve connecting the points D and A. The total work done in the two processes is the sum of the work W'3 and the work W'4. Since the direction of the integration along these two curves indicated by the arrows is negative, the integrals, that is the areas under the curves, are also negative. As a result, the total work done in these processes is negative. Since the total area obtained in the first two integrals is positive and the total area obtained in the second two integrals is negative, we can conclude the following. The net pressure volume work W' done by the system in Carnot cycle is given by the difference between the total area of the two plane figures under the curve connecting the points A, B, and C and the total area of the two plane figures under the curves connecting the points C, B, and A. This difference is simply equal to the area of a plane figure defined by the closed curve connecting the points A, B, C, and D. We can also interpret the work W' done in the whole cycle as a function of a set of parameters characterizing the cyclic process. By applying the first law of thermodynamics, we can immediately see that the work done in a thermodynamic cycle is always equal to the heat exchanged between the system and the surroundings, since the internal energy of the system is the same in its initial and its final states. That is, the work W' done by the system is equal to the heat Q1 absorbed by the expanding gas minus the heat Q'2 released by the gas during its compression. Therefore the heat Q1 and the heat Q'2 completely determine the work done by the gas in Carnot cycle. However, other parameters describing the process are more convenient to measure. We have shown that the work W' done in the whole cycle is also equal to the mass m of the gas times its specific gas constant Rs, times the difference between the maximum absolute temperature T1 and the minimum absolute temperature T2 of the gas, times the natural logarithm of the ratio of the final volume VB of the gas to its initial volume VA in its isothermal expansion. In this case, the mass m of the working substance together its specific gas constant Rs are determined by the given amount of water vapor used in the steam engine. Another parameter chosen by the design of the engine is the difference between the maximum and the minimum temperatures in the cycle, which are determined by the hot and cold reservoirs brought into contact with the working substance. Finally, the ratio of the final volume of the working substance to its initial volume in the isothermal compression is also a parameter, which can be determined by the geometry of the cylinder and the moving piston of the steam engine. We can also apply a symbolic notation for the exchange of energy between the system and the surroundings in Carnot cycle, which indicates the direction of the transport of energy in the pressure-volume diagram. In the first process, where the gas undergoes an isothermal expansion between the states A and B, the expanding gas absorbs the heat Q1, which can be represented by an arrow pointing inside the plane figure defined by the closed curve connecting the points A, B, C, and D. Its direction indicates that the heat Q1 absorbed by the gas contributes to the internal energy stored in the system. The work W'1 done by the expanding gas reduces the internal energy of the system, which is indicated by the arrow pointing outside the closed curve representing the path of the cycle. In the second process, where the gas undergoes an adiabatic expansion between the states B and C, there is no exchange of heat but the expanding gas still does the pressure-volume work W'2, which reduces the internal energy of the system. Therefore the arrow representing the work W'2 points outside the closed curve connecting the points A, B, C, and D. In the third process, where the gas undergoes an isothermal compression between the states C and D, the gas releases the heat Q'2, which is represented by an arrow pointing outside the plane figure defined by the points A, B, C, and D. Its direction indicates that the heat Q'2 released by the gas reduces the internal energy of the system. The negative work W'3 done by the gas during its compression increases the internal energy stored in the system, which is indicated by the arrow pointing inside the plane figure. In the fourth process, where the gas undergoes an adiabatic compression between the states D and A, there is no exchange of heat but the gas does the negative pressure volume work W'4, which increases the internal energy of the system. Therefore the arrow representing the work W'4 points inside the closed curve connecting the points A, B, C, and D. We have seen that the work W'2 and the work W'4 have the same magnitude but the opposite sign. Therefore the arrows W'2 and W'4 have the same length, but the first one points outside the closed curve and the second one points inside the closed curve. As a result, they cancel each other out. Only the work W'1 and the work W'3 contribute to the net work W', which is produced by the conversion of the net heat Q1 minus Q'2 exchanged between the system and the surroundings. Now we can summarize the process of conversion of energy by a steam engine operating in Carnot cycle. In Carnot cycle, the water vapor absorbs the heat Q1 from a boiler, which is a hot source at the absolute temperature T1, and releases the heat Q'2 to a condenser, which is a cold sink at the absolute temperature T2, and is the net work W'. The thermal efficiency Eta of Carnot cycle is defined by the ratio of the useful work W' to the heat Q1 delivered from the boiler. Since the heat Q1 is equal to the work W'1 done by the body of the water vapor during its isothermal expansion, we can write that Eta is equal to W' divided by W'1. We have already determined the quantities in the numerator and the denominator of the fraction. Then we can write that Eta is equal to the mass m of the water vapor, times its specific gas constant Rs, times the difference between the temperature T1 and the temperature T2, times the natural logarithm of the ratio of the final volume VB of the vapor to its initial volume VA during its isothermal expansion, divided by m times Rs times T1, times the natural logarithm of the ratio of VB to VA. By simplifying this expression, we obtain T1 minus T2, divided by T1, or 1 minus the ratio of T2 to T1. Then we can conclude that the thermal efficiency of a steam engine only depends on the temperature of its boiler and its condenser. The higher the absolute temperature T1 of the boiler and the lower the absolute temperature T2 of the condenser, the greater thermal efficiency of Carnot cycle is. The maximum value of Eta is equal to 1, where we have 100% thermal efficiency. In such a case, the heat Q1 delivered by the hot reservoir is completely converted into the mechanical work W' without any loss, that is the heat Q'2 vanishes. However, the formula for Eta implies that 100% thermal efficiency would be possible only if the condenser or the cold reservoir were at absolute zero, that is the temperature T2 were equal to 0 Kelvin. In fact, it is impossible from both practical and theoretical reason, and the value of Eta is always less than 1. As a result, in Carnot cycle converting the heat into work with some loss, only a fraction Eta times Q1 of the heat Q1 delivered by the boiler or the hot source can be converted into the work W'. The rest of it, which is equal to 1 minus Eta times Q1, is released to the condenser or the cold reservoir. We have seen that Carnot cycle is an idealized thermodynamic cycle of steam engines. Carnot cycle can also be considered as a model of a heat engine, which converts the heat Q1 delivered by the boiler or the hot source into the work W', while the heat Q'2 is released to the condenser or the cold sink as a loss of heat. Although the operation cycle of real heat engines is not exactly a Carnot cycle, the thermal efficiency introduced in this model is not merely a quantity describing a conversion of energy in a theoretical process. It plays a crucial role in thermodynamics, since we will demonstrate that Eta, which is equal to the difference between the absolute temperature T1 of the hot source and the absolute temperature T2 of the cold sink divided by T1, provides the maximum of the thermal efficiency of any kind of heat engine. We can also reverse the direction of Carnot cycle, where the cycle is performed through the thermodynamic states A, D, C, B, and again A. In the processes between the states A and D, and between the states D and C of the reversed Carnot cycle, we apply an external pressure somewhat less than the pressure of the gas in the cylinder. In the processes between the states C and B, and between the states B and A, we use an external pressure somewhat greater than the pressure of the gas. As a result, we only change the sign of the heat exchanged and the work done in the cycle, that is, we reverse the direction of the transport of energy in the process. In the reversed Carnot cycle, the gas absorbs the heat Q'2 from the condenser and releases the heat Q1 to the boiler, while external forces do the work W on the gas, which is equal to minus W'. Such a reversed process has two different applications. The first one is the heat pump used to control temperature in enclosed spaces by heat transfer. A heat pump extracts the heat from its colder surroundings at the absolute temperature T2 and transfers it into a warmer place held at the absolute temperature T1 by using the external work W. We describe the efficiency of this process with the coefficient of performance denoted by COP with the subscript H, that is heating, which is defined by the ratio of the magnitude of the heat Q1 to the magnitude of the work W'. This fraction is equal to the absolute temperature T1 divided by the difference between the absolute temperatures T1 and T2. The second type of application for the reversed cycle is the refrigerator, which removes the heat from the place held at the absolute temperature T2, and transfers it to its warmer surroundings at the absolute temperature T1 by using the external work W. We denote the coefficient of performance for refrigerators by COP with the subscript C, that is cold, and define it by the ratio of the magnitude of the heat Q'2 to the magnitude of the work W', which is equal to the absolute temperature T2 divided by the difference between the absolute temperatures T1 and T2.